Hi everyone, just wanted to take a moment to talk about the final component as we're getting into our formal proofs, um, how we can extend our proofs into geometric concepts, right? So before we were dealing with paragraph proofs of really kind of whatever we were dealing with, and we were starting with the words, then we used some of the appropriate like orientations and notations for the algebraic components that we knew pretty well. And now we're going to extend those into the geometry concepts. So these are kind of a little bit more akin to what we're going to be dealing with going forward. So some of the things are still the same, right? So the reflexive property, the symmetric property, and the transitive property, they all still hold for segments and angles. So they are still valid reasons that you can use going forward, right? So as you can see here, we're still now given um, information, though now we are given angles. One of the important components of this one is that we are given several different things, and we're putting them on two different lines. You could have put them on one line, you can put them on two, doesn't matter. But ultimately, you have two different lines of givens here. And by the transitive property, which you can still use because the transitive property does still apply to the angle measures, you can say that the measure of angle 1 is equal to the measure of angle 3. Okay. So these are still going to work, and you can still apply them to geometric concepts. So let's kind of look at what does that mean. Well, if we were to do something like this, we can still set up, just got very laggy, sorry. We can still set up our two columns. And I'm going to start my statement, okay, my statement and my reasons. Now, we always are going to start with what we are given. What are we given? Well, we're given two pieces of information. PQ is congruent to QS. I'm just going to put these in one statement. QS, segment QS, is congruent to segment ST. So again, we do have to still be careful with our notation. Again, if you are having difficulty typing something like this, you can just write it out. You could write out in words, segment PQ is congruent to segment QS. Obviously, you want to try and be able to use the notation as much as possible. And if you can't, just do your best. So the reason behind that is given, right? We're still starting with our given. 2, what can we do now? Well, whenever you get something like this, I can tell you right away that one of the things that we can use to do this, if we have to do this, is we can just say that the measures are equal, right? By the definition of congruence. So QS is equal to ST. And the reason we're able to say that the measures are equal was because, well, we knew that the segments were congruent, and therefore we can say that by the definition of congruence, okay? By the way, one of the other things I will recommend is, if possible, mark off these different things. Write it down, draw a picture, something, so we know that PQ and QS are the same. We know that QS and ST are the same. So our goal is ultimately to show that the 1 and the 2 here are the same. You can see very clearly it is, but let's go through the formal steps to finish it off. All right, so let's finish it up. Well, we're actually almost there. We're going to do this in 4 steps. So, right, PQ equals QS, QS equals ST. Well, what can we use? The transitive property, right? Yes, so we can use the transitive property. Transitive. And then finally, same type of concept here. PQ, segment PQ is congruent to segment ST. And that was done by the definition of congruence. Okay, now I am done. Or you could again use QED. So all we did was the same arguments that we were making before. Now we just applied them to geometric properties. This is actually kind of a, oh, I went one step further than I needed to. I'm sorry. I was supposed to just end at this step. I could have ended there. I went one step further. So I didn't even need to do that. But ultimately, okay, so it would have only been these three. I guess I just assumed we were going all the way back up to congruent segments. But anyway, the measure of the segments is the same, so we should have stopped there at 3. But ultimately, that's fine. You can see what we could do if we kept going a step further. I actually got a little ahead of myself because what we are now looking at is the reflexive property, symmetric property, and transitive property of congruence, right? So they work for equality, so A is equal to A, but as it turns out, they also work out for congruence. So segment AB is congruent to segment AB. You can use symmetric for them. So segment AB is congruent to segment CD, then segment CD is congruent to segment AB. And similarly, the transitive property of congruence does hold. Actually, what I just did, because I went one step too far on this one, was I actually just proved the transitive property of congruence. So congratulations. In case you ever want to know what the transitive property of congruence proof looks like, well, we've just went through it. But ultimately, if we were given something like this, we should have stopped it one step above. I gave more information than was needed. All right, so again, why are these properties true? Well, I just showed you this transitive property of congruence. And here's the symmetric property of congruence. As you can tell, really all we're doing is we're starting with what we're given, using the definition of congruent segments. You did that, and then using the symmetric, the reflexive, the transitive property of equality, and then going back up to the segments, being congruent. All right, so same kind of concept. I just showed you how to do it for transitive, and you could do the same thing for reflexive. Okay, so what are we going to use? Now, this postulate, the segment addition postulate, ultimately comes up a lot in future geometric proofs. So we're going to start off with using some proofs involving the segment addition postulate, and understanding what it means is going to be really beneficial for your later on use. So if A, B, and C are collinear, so they're on the same line, then point B is between A and C if and only if, so here's our biconditional, so means we can go both ways. If and only if A plus B equals AC. So what does that ultimately mean? That means the two things, right? Remember the biconditional statements, they meant two different things. So it means this way: if A, B, C, and B between, then AB plus BC equals AC. And it also means the other way. So if AB plus BC equals AC, then, oops, AB and C and B between. All right. And if you ever want to know which one is the between one, look for the one that comes up in both, right? And then it's not in the final. So B is in both, it is in between. Okay. So really all this is saying, and you're going to get to practice a little bit with some of the measurements, is just saying if I have this part, like let's say this was x plus 2 and this was x, and the whole thing was 23, we could say that x plus 2 plus x is equal to 23, and solve it and so on and so forth. That's really all it's saying. But this is ultimately very useful to proofs later on. It's really just a fundamental concept, and that's why it is a postulate. It's just true, right? That's just what we are accepting it as. So here's an example involving it. Again, we're given the pieces of information that segment AB and segment DE are congruent. We're also given this other one, which we use a little bit later. And what's the first step we're always doing here? Just kind of take note of this. So other than starting with the given, we're then using the congruent segments and just rewriting them as measurements, right? It's a lot easier to do things with measurements than it necessarily is with congruent segments. So then we can use the additive property. Once we use that, we can use the segment addition postulate. So this is going to be a common occurrence, right? We add things together. Oh, segment addition postulate. Okay. Substitution. Bam. We can say that they are congruent by the definition of congruent. So all we essentially did was we just kind of added these parts on because we knew that they were equal. And we were able to do this because we knew they were equal, right? So ultimately, you just need to be careful, right? Because we know they're equal, we can add them together. And then from the diagram, we knew that this plus this equals that by the segment addition postulate. Okay. So you just need to be careful, right? This step right here, that's where we're using the segment addition postulate. And that's coming right from up here that we can see visually. AB plus BC equals AC, DE plus EF equals DF. And that is ultimately what we then substitute for, right? We know that this was equal to that, therefore I can just substitute that with AC. This was equal to this, so I can substitute this with DF, and that's where I got to substituting, all right? So let's try it. So obviously, first thing that we are told is the given. Okay, now what are we going to do? Definition of congruent segments. So all we're going to do is just going to rewrite them as the measurements. SU is equal to LR. TU is equal to LN. Okay, definition of congruent segments. So let's see, what do we have here? SU is equal to ST plus TU. LR is equal to LN plus NR. Well, this is really kind of what we were just talking about. This is the segment addition postulate. So segment addition postulate. Okay. As you can see from the diagram, this is quite apparent, but ultimately our reasoning behind that is the segment addition postulate. Additionally, the other piece of information that I think you can kind of gain from this is, as you can tell, we're kind of combining things together into steps, right? We're using the same reasons. Why use an extra line? So we're saying that these two, we're going to ultimately use the same thing, right? Same argument of segment addition postulate. So let's just add them together. Now, what exactly are we doing here? Well, we are substituting. All right. So how did we get from here to here? Well, what did we know about TU and LN? Well, we know that they were the same. Therefore, on this one, essentially what we have done is replace the TU with the LN. So we did another substitution. All right. Now, finally, we are subtracting the LN from both sides. So I'm going to subtract, which is ultimately leaving you, bam, that cancels and that will cancel. So I'm going to get ST is equal to NR, and by the substitution property. And then finally, we know that segment ST is congruent to segment NR. And what is that going to be? Well, the same thing that we did up there. That is the definition of congruent segments. Could have just used the definition of congruence as well. Okay. And the other piece of information, let's do this last one, make sure we're all set, just so you can see another one. So once again, we are given this piece of information. And then what's the first thing we're doing? Once again, we are using the definition of congruence. Finally, PQ plus QR is equal to PR. That is the segment addition postulate. Now, what are we doing? We obviously, our goal here is to get a PQ and an RS, so somehow we have to introduce this. So, well, what can we do? We can do SR or RS plus RQ, right? QR plus RS is equal to, what's that equal to? QS by the segment addition postulate. Again, we know that PR and QS are exactly the same from the definition of congruence. So now we can just set them equal by substituting. When we're subtracting, we're going to subtract the QR from both sides. When I've run out of room. Okay. So we're just subtracting QR from both sides. And then finally, what are we left with? Well, ultimately, at least I ran out of room. We'll just shorthand that. So we're just skipping a little bit. PQ is equal to RS. So we know that PQ is congruent to RS. Now, we do need to be careful, obviously, since they're giving us the statements and the part of the statements and part of the reasons in this particular problem. You just need to be apparent with the actual information that you were given. Like I gave you the full written out subtraction property, but then when I saw what the final thing was, it didn't make sense for me to write it all out that way. It made sense for me to just write it after having simplified. So I did that. That's why I erased that last one. But ultimately, I hope this gives you an idea of a similar type of process that you're going to be taking to get some of these problems done. I think the hardest part is after you've done, well, the hardest part is ultimately figuring out, well, what comes next, right? So obviously, once you come up with a statement, it's usually not bad with coming up with a reason, but sometimes the hardest part is figuring out what comes next. And if you're ever in a situation where you don't know what comes next, go back from the bottom and just kind of work your way up and see what you can do, right? So if you know that the definition, you know at the end you're going to have this statement, right? And then kind of go one step up, see what you know would have likely come before then. And that's kind of one way that you can think about this. So there's a lot of different things, and we're going to practice a lot with proofs, so don't worry if you're not, super fantastic at it right away. But please let me know if you have any questions. Have a good night.